And for those of us that were not able to ask our question, or the questions were not taken, if possible, if there's any, then you still have the privilege to get your question answered if you ask. Meanwhile, you could see that the time was not enough for Prof to do justice to. Sorry, let me take that. Not to do justice, to finish everything. And the fact remains that even if he's given 10 days, he cannot finish what he think he want to teach us. We implore us that intermittently, periodically, we should be visiting our YouTube. Nearly all the classes are on, if not all, they are on our YouTube channel. Please visit, you stream, you watch them without at your own convenience. Please and please, whatever we are able to grasp, because of time limit, his prof is well loaded and well prepared, but the time which has been an enemy of human being will not permit. But also, the little one is able to teach us, we can also augment it with all the other resources that are already on our YouTube channel. The link is on our platform. And also, I will share the WhatsApp link of our normal Saturday classes or of our general platform. For those of us that are new on this platform, that are not on our platform, I will share the link. You can join. But if you are in one or two or three, please, you don't need to join the other one, so that we allow other people to join. Thanks so much, Paul, for the privilege. You can commence your class.
Good afternoon, everybody, and you're welcome back on board this learning platform. The second segment of today's training, the afternoon section, should we call it. So we are going to look at what I call a tour of selected classifiers. We want to look at selected algorithms and see what we can do with it. And hopefully we'll be able to go into detail of at least one of these algorithms, and then also practically demonstrate how you can run your first machine learning model, build your first machine learning model in a weaker environment. So let's follow. By now we already discussed, and we should be very comfortable with when we talk about machine learning modeling framework that support the let the data speak idea. So whenever you have a problem to solve, always remember this. So it's an iterative process. Iterative. So you can always come back. So don't do too much pre-processing. Do your modeling, select the algorithm, start from simple to complex. This is the principle to note. So once you model it, you can always go back, do a hyperparameter optimization, tune the algorithms, change the algorithms to another one if there's need for that. If after all this, nothing is happening, you can also go back. Feature engineering, feature selection, PCA, outlier, normalization, so many things you can do. Always use the iterative process so that you may let the data speak. Don't prejudge your data. Don't assume support vector machine will work for this data. You may be wrong. So start simple and then progress to more complicated or sophisticated algorithm. Always remember this fact. Now, so we will look into data exploration learning. This is where we are. We want to take an example of this classification problem. Supervised learning. We want to look at it. We're going to evaluate it by checking the recall precision, see overfitting or what. So we're covering the classification part. So we said classification is a data science task for predicting the value of a categorical variable, target class. We call it target or a class, by building a model based on one or more numerical or categorical variables. Now we'll discuss this. There are majorly four groups of classification algorithms. We have the one that is based on frequency table, the one of covariance matrix, the one that is based on similarity functions, and then we categorize the remaining one to others. That doesn't follow any of this. They have their own principles. Like support vector machine is falling under the others. In the frequency table, you have the 0R, the 1R, the naive Bayesian decision tree. You make a frequency table of your data, and then you can build these algorithms accordingly. We have the one of covariant matrix, like linear discriminant analysis, the logistic regression. We also have the similarity function, like K nearest neighbor. This is going to be one of the example we're going to look into today, K nearest neighbor, because it's very straightforward. It's very easy for people to grasp. Show me your friend, I'll tell you the kind of person you are. If out of 5 friends you have, 3 of them are corrupt. Only 2 of them is okay. You are likely going to be classified as being corrupt because majority of your friends are not good. So that is the idea behind K nearest neighbor. Your nearest neighbors will determine who you actually where you actually belongs to. And then the one we categorize as others, example include artificial neural network, support vector machine, and host of other algorithms. Now, so the list of algorithms, like I mentioned in the last section, is so wide. KNN, naive Bayes, decision tree, support vector machine, logistic regression, etc., etc. How does classification work? See, let's say you have this data. This is a student grade. This is the result. 5 fail, 6 pass, 2 fail, 7 pass. So we have this pass result. This is past data. We want to build a classification model that whenever you have a new set of students, just give this model to them. It will print out this student will pass, this student will fail. So what do we do? Our classification algorithm will study the data and try to come up with, remember I said hypothesis function, it will be age 15. Which year now? It is this. This is the hypothesis function for this simple problem. It says, if CS is less than or equal to 5, then result is fail. Otherwise, it will be pass. It studied, this is the data, this is the training data. It has studied the training data very well and notice that whenever there's something that is less than or equal to 5 fail, but 6 pass, 7 pass. It means anything less than or equal to 5. So this is the hypothesis function for this model. Very simple one. Now, when you have a test query, somebody scored 8, you compare it with this hypothesis function, and it will generate result because it is said the result is pass. This is a very simple example of how classification algorithm work. You may have data set that is so simple that a simple if-else statement will solve your problem. And that is the hypothesis function. You finish it and you can go. However, sometimes it could be more complicated than we thought. Another example, you can see here, you have the training set, attributes, another attribute, and then another attribute. The class is yes, no, yes, or no. Maybe, should you give loan to someone or not? So we see training procedure as more of an induction process. This is learning algorithm. After learning it, the opposite is deduction. We go from the model we built to now try to classify the new testing sets. We now classify, we know the classes they belong, but we will hide it from the experiment. We hide it from the model. We want the model to tell us the result. We now compare the result in our hand and be able to compare how far this model is doing. If it's really wonderfully doing well, Then we can then adopt it and then deploy it as a final model that will be helping us to identify subsequent or future cases. So the classification process basically has two steps. We have the step one, which is model construction, where you're going to describe a set of predetermined classes. So each sample is assumed to belong to a predefined class. So then the samples are used to build the model. We call it the training set, as I've explained. After you've trained the model is then represented by a classification rule, a decision tree, or a mathematical formula. Then the next step is to use the model. Once you build the model, now it is time for you to test it, and then you can then continue using it if it does satisfy your testing criteria. So let's look at another example of a classification problem. Look at this. We want to classify professors into tenure or not tenured. Tenure is more like a confirmed academic staff. If you're a professor, you just spent 3 years, you are not confirmed. This does name. We don't need the name for training. It's just there for identification. And usually when we request for data, we request for anonymized data. Data that does not contain name or means of recognizing the person. Take note of that. So this is the first variable, the attribute 1, attribute 2, and this is the target. Assistant professor, 7 years is tenured. This is the training set. With this training set, we expose our classification algorithm to it. It was able to build this hypothesis function that worked. If rank is equal to professor or year is greater than 6 years, then it's going to be tenured. If you're a professor, irrespective of number of years, you are going to be tenured because you're already a professor. That's all. Or, look at the or. Or if you have a year that is greater than 6, irrespective of your status, either associate or assistant professor, you are going to be tenured once you spend more than 6 years. This is the very simple classifier we built. Now, when we have a new set of professors we want to testing test, what we built before we bring it in. If you're a professor, you are going to be, yes, tenured. Associate professor, you're not tenured. Automatically, we check your age, number of years. You are not up to 6. No. You are not up to 6. No. This one, assistant professor, 7 years. Yes. You see, you can be able to classify new cases. This is how classification algorithm works. Now, we have other ones. You want to take loan decision. You want to build it for a banking system. You have training data set. You want to know it's a youth. The age is youth, middle age, senior. Income is low, high. Loan decision, risky. Why are youth risky? This one is risk is safe. You can give loan to him. It's middle age, risky. Why is this risky? Is it because of income or because of the age? Medium, safe. So this is the classification rule now. Adopted, this is the hypothesis function. Adopted in this case. If age is equal to youth, then loan decision is risky. If income is high, then loan decision is safe. If age is equal to middle age and income low, then loan decision is risky. Based on this, hopefully, subsequent test sets, you can classify them accordingly. That is how you build classification. You build classifiers. Yeah. Now, sometimes it could be more complicated than this. They have to go deeper to more sophisticated algorithm, especially if the problem is not linearly separated. Then we have the eager learners, type of learners. In classification algorithm, we call some eager learners and we would call some lazy learners. The eager learners, they generalize model from training data. Generalized model is constructed from training data. Then using the model, the class of tests is predicted. So they take longer time for training because they are going to build the model. They take longer time for training and less time for prediction. Once you train them, it can take you so many time, minutes, hours. But once you build them, testing becomes very easy because they just pick in, take your sample, and tell you where they belong. Example include decision tree, naive Bayes, artificial neural networks, support vector machines, and their families. They are called eager learner. Then for the lazy learner, they store the training data. They don't build any model. When you have new sample, you want to query the similarity between the test data and the training set, they actually try to calculate the class of the test data from the stored training set. We also call them instant-based learning. In comparison to eager learner, lazy learners, they have less training time because they are not really doing training. They just store data. And then when you have test case, they try to compute the distance between them, as we're going to see in case of k-nearest neighbor. But prediction takes more time for the lazy learner because they don't learn anything. They just store the data. It's when you have to do prediction, they bring in the training set and try to compare with the test set and then see where it belongs. Example include k-nearest neighbor and case-based reasoning. It comes to different types. Now, let's look at our first example of algorithm, KNN. What is KNN? How does it work? How do we choose the value of K? Examples, advantages and disadvantages of the model. In k-nearest neighbor, it is one of the simplest supervised machine learning algorithms that are mostly used. One of the simplest. Remember, I always tell you, start from simple algorithm and progressively move to more complex algorithm if the need arises. So it KNN classify a data point based on how its neighbors are classified. That's why I said, show me your friend. I will tell you the kind of person you are. The KNN store all available cases, all the training set are stored, and the classifier new cases based, the classifiers new cases based on similarity measures. So a lot of application of this simple algorithm have been deployed successfully in statistical estimation and pattern recognition systems. K in the KNN is an hyperparameter that refers to the number of nearest neighbors to include in the majority vote process. What we do is that I look for the three closest neighbor to you. The three closest neighbor to you, I look for them. Out of these three, two of them are good guy, one of them is a bad guy. 2 against 1, we vote. That will be 2 against 1. That means you are a good person. And that is why we try to avoid voting having tie. So if the number of classes you want to classify is 2, you don't use even numbers. You don't use 2. If you set K to be equal to 2, one neighbor is good, the other neighbor is bad. Where are you going to categorize the person? It's not going to be possible. So you have to always make sure that you don't form a tie when you vote. When we have 3 classes to classify people to, then it means you cannot set your K to be multiple of 3 because it's going to form a tie, or it could form a tie. We're going to talk about that later. So the K is an integer. If K is 1, then K is assigned to a class of single nearest neighbor. Sometimes we start with 1, it's the default value. Your nearest neighbor is what we are going to categorize you to. The nearest neighbor. If it's good, you are good. If it's not good, you are not good. Only one neighbor. And surprisingly, in some application, we found case equal to 1 to be the best hyperparameter value we can use. When you try to do hyperparameter tuning, you get worse results. 3 bad, 5 worse, 7 worse, then we go back to case equal to 1. And in some application, by the time you do hyperparameter tuning, you find out that you got the best from 11, k is equal to 11. That is why machine learning is not a dogma. Don't assume what's going to be the value of k. Some people will advise the best k are usually between 7 and 11. I said no. It depends on the data you are actually modeling. You'll be surprised. K is equal to 1 may work for you, and that is why you have to compulsorily do hyperparameter optimization. Now, moving further, how does k-nearest neighbor work? How do we calculate the similarity? You know, now we say it calculates similarity between new samples and the training set. So in k-nearest neighbor, it should be noted that we have distance measures, another hyperparameter to be considered. We have Euclidean distance, Manhattan distance, Minkowski distance. New distance measures are coming. You can also build your own distance measure. This formula for Euclidean distance, Manhattan distance, Minkowski. Sometimes when you shoot k equal to 1 with Euclidean distance, you may get 60%. When you change it to Manhattan, it may become 65. You have to check which one is working for this present data. That is what we call hyperparameter tuning, or some people call it hyperparameter optimization. So in the instance of categorical variables, when you have categorical variable like male, you can't calculate the distance between male and female. It's not a number. If it is 7 and then 8, we will see example shortly. You can calculate the distance between 7 and 8. But now it is male, female. How do you calculate the distance? We are going to use what we call Hamming distance. The formula is this. If x is equal to y, distance is going to be 0. Male, male. If x is male and y is male, it's going to be 0. Because there's no difference between them. If x is not equal to y, that is, you have male in this variable and female in this variable. Under this variable, it will be 1. This is the formula. We call it Hamming distance measure. We use it when you have categorical variable in your data set. And it happens sometimes. Now, this is how KNN works. See, the step one, calculate the distance. When you have a new sample, you already know your training set. It has class A and class B. Class B in green, class A in red. New example to be classified as be given. Once you have gotten your training set, you store it in the memory. When now the testing set arrives, this one, we don't know where it belongs. It arrives. Then you calculate the distance between this and every member of this training set. From this to this. Calculate the distance from everything. All the available training sets. Find the closest neighbors and vote for the labels you are going to categorize this new sample to. See? These are the 3 steps. Calculate the distance, find the closest neighbors, and vote for the labels. Now, when you calculate it, first of all, you calculate the distance between this and everything. And that is why when you have testing set for k-nearest neighbor, it takes time. Because imagine having 1,000 samples. You are going to calculate distance between this new unknown sample and the entire 1,000 training sets you have. When you have another new testing set that you don't know, you do the calculation again. Every time you have a new sample, you keep doing the calculation. So that's why if your data set is huge, it may not be a good option for you to try out because it's going to take time to do the calculation. But sometimes it's worth it to test it out. Maybe it will be what you need to get better result. Now, so once you calculate the distance between these and every other members, we now decide, okay, how many members have calculated the distance between the new sample and all the other, every other samples in the training set. I will now decide what is the value of K to vote. Okay, let me vote with K is equal to 1. I want to choose only K is equal to 1. You start from 1. The nearest person to this guy is this. So I'm going to push. No, I think it's this. The nearest person to him is this. I'm going to push this guy to class B, green class, if I'm using K is equal to 1. However, if I'm using K is equal to 3, then you're going to see what are the three people that are closest to this. 1, 2, 3. This one is closer, closer, closer. These are the 3 closest to this guy. Out of these 3, 2 into green class and 1 into red class. I'm going to categorize this into green class again. Then I check it again, K is equal to 5, until we see which one is working for us. So when you check K is equal to 1, you do it for all the testing cases and see the result you are getting. Or validation case. When you say K is equal to 3, check it again. K is equal to 5. This is how you are going to determine what is the final value of K to be used. Note that your testing set is not being used for this. Your training set is going to be used. Either you divide your training set into training and validation set, or you use the cross-validation fold method to do the work. So this is how KNN actually works. The algorithm is choose K. For a given new instance X new, find K closest training point with respect to a distance measure. Don't forget the distance measure we already identified. Classify X new to the majority vote among the K points. How to choose the right K? We call it parameter tuning. There's no value of K that is better than anything. See, you have to try and see which one works for your data. I ask you to use let the data speak approach. Start with K is equal to 1 and keep changing it. Keep the distance measure constant at Manhattan. Okay, keep changing this. And then once you are done, come and try another distance measure. Maybe it's to also work for you. Sometimes we can use grid search. In grid search, as you are changing K, you're also changing the Manhattan, the distance measure. But that will take a lot of time. You see, that will take a lot of time. So, because that will be, you have to try every options. As you are changing K, you're also changing the distance measure. K is 1. Manhattan, what's the value? The other one, what's the value? Minkowski, what's the value? You check everything out until you are able to get which one is getting the best value for you. This is distance measure M, distance measure, another one, another distance measure. And your K is varying. K is equal to 1, 2, 3, 4, 5, 6, 1, 3, 5, 7, there. So choose the optimal value of K. That is, so check your data and try to see. People say in general, a large K value is more precise as it reduces the overall noise. However, experiments have shown that sometimes depend on your data set. We've had K is equal to 1, giving us the best result. In other class, we've had K is equal to 7, giving us the best. We've gotten K is equal to 11. So that is why whatever recommendation is given is just an advice. But always let the data speak. You can see here, it's saying historically, the optimal K for most data set has always been between 3 and 10. For most data set, historically. But that does not mean the data in your hand will not work for K is equal to 1. So don't throw away 1 because you read somewhere that it's always between 3 and 10. Look at it, they say most data, not all data. If you say all data set, we say it's wrong. Because me personally, I have had cases whereby K is equal to 1 worked for me. So let's take note of that. Tips. Choose are not K value for 2-class problem. I've mentioned that. Why? Because we don't want to have a tie. When you are voting, you don't want to have a tie. 1-1, 2 against 2, 4 against 4. No. So K must not be multiple of number of classes. This is the final stop. See, when you have 3 classes, you don't choose anything that's a multiple of 3. You cannot choose them. Because if you choose 9, they can add 3, 3, 3. When you vote, you don't know where you're going to push the new sample to. The main challenge of KNN is the complexity in searching the nearest neighbor for each sample. For every sample, you have to search, calculate the distance, and also search for the nearest neighbor. So it makes it to take a lot of time, and this is the disadvantage of lazy learner. Let's see this example. You can also practice it in your own. I want you to understand at least one of the algorithms, see the flavor, how it works. It's not magic, okay? You can also develop your own algorithm and see how we can use it, and others can also adopt it in their day-to-day predictive solutions. Yeah, look at this example. Consider a data set having 2 variables. We have math grade and CS grade. 4, 3, this student failed. 6, 7, he passed. 7, 8, pass. 5, 5, fail. 8, 8, pass. Now, we want to see what of 6, 8. Is it going to pass or fail? This is the testing set. You see, based on this data, we must classify the unknown as pass or fail using KNN. How do you determine? This is training set. It gives us this training set now. Now we want to decide what is the output of this. Is it going to pass or fail? Now, let us build a k-nearest neighbor algorithm together. Remember, the first thing you have to do is to calculate the distance. We are going to use Euclidean distance. We are going to use Euclidean distance. This is very straightforward. You know, under math, we have 4 and 3. So you go to Euclidean distance formula, calculate that distance. Okay, I'm going to put 4 here, put 3 here. Okay, that's Euclidean distance. 4 here, 3 here, and then you're going to square it and then find the square root. If you solve the problem, you're going to have these numbers we have here. So if you solve for the first one, using the Euclidean distance, you get this value. This is the distance between. So I calculate the distance between this guy and this guy. Once you are done, you calculate the distance between this guy and this guy again. So you see here is 4, and then it is what? 6. 3 against 8. That's how you're going to apply it to the formula. The formula is there. You can see it has sigma. We are dealing with just 2 items. So you see where x is. The first one is 3. You see 4. 4 minus 6 squared plus 3 minus 8 squared. Doesn't matter that you put 8 beginning or 3 beginning, because square is going to cancel the negative. Then finally you're going to have the square root. So do the mathematics, you're going to see it. 4 minus 6 is going to be 2 squared plus 3 minus 8. That's going to be minus 5 squared. That'll be 25. It's going to be 4. 4 plus 25 is going to be 29. By the square root of this, we're going to have 5.3. That's the square root of 29, 5.385. This is the distance between this sample and the one we want to calculate where it belongs. Do the same calculation for this. You get 1. You can check it out. Because distance difference between this is going to be 0. That will be 0 square plus 8 minus 7. That will be 1. 1 square is going to be 1. The answer is 1. The same thing here, you have 7 and 8. Check them out, 1 and 0. The 0 square is 0 plus 1. That 1, square root of 1, 1. For this one, do the procedure. You are going to get 3.16. For this one, you're going to get 2 using Euclidean distance. If we use Minkowski distance, this measure will be different. And that's why you have to specify which one you are using. Now, having calculated this, the next thing for you to do now is to decide, okay, this one, this is the distance between this and this. You now arrange them in ascending order. The smallest on top. This guy is the one on top. This guy is next to it, because they are both 1 at the same level. 1, 2. Next to it is this guy. Sorry, number 3, number 4, number 5. You arrange it in an order of size, the smallest in front. Okay? So, because if I want to use, if k is equal to 3, then the selection will be this. Let's say we want to use k is equal to 3. We are using this, and this only. 3 samples. Now, this sample has pass. This one pass. This one pass. That's going to be 3 pass against 0 fail. It means we are going to vote that this guy belongs to pass. I want to use 5. Okay? I'm going to have 3 passes and 2 fails. 3 against 2. Majority still cast the vote. This guy is going to pass. Therefore, we can conclude that based on using k is equal to 3, we conclude that this guy is going to pass. If I use k is equal to 5, it will still be pass. This is how we decide. If I bring in another problem to solve, 9, 7. Tell me, is it pass or fail? You have to pass through the same procedure. You calculate the distance between this and this, between this and this, between this and this, and then arrange them in ascending order. And then, based on k is equal to 3, you want to use or k is equal to 5, you decide if it's going to pass or it's going to fail. This is how k-nearest neighbor was practical sense. So, I also give you activity to try out on your own. You have, this is a weight, height. This person is categorized as underweight. Normal, underweight, normal. So I'm giving you this. I want you to use k-nearest neighbor to classify for me, is it normal or underweight? You have to pass through that procedure. Calculate the distance between this and this, that and this, each of them, and then you can then decide. I said, choose different value of k, work for 1, tell me the result, work for k is equal to 3, and work for k is equal to 5. That is, you are solving it using k-nearest neighbor. So sometimes I request people to do this so that when we go to software now, software will do all these things for you. You don't need to bother yourself. But I want you to actually understand how it is working, it is being done. So for those who really like to be very inquisitive, they like mathematics, you can come up with your own distance measure. If we use Manhattan distance, it will be different calculation we are getting. If we use Minkowski distance, there are so many other distance measure. You can even create your own distance measure and use it on k-nearest neighbor. If it's working fine, getting out better result, you can popularize it. People will start using it also as your own little contribution to knowledge. This is how k-nearest neighbor works. Now, the pros, k-nearest neighbor is simple to implement. It executes quickly for small training data set. Yes. Doesn't need any prior knowledge about the structure of the data in the training set. No retraining is required if the new training pattern is added to the existing training. Sometimes as you are building your model, your client decided to send you new samples. Just add it to it. You don't need to do any retraining because it does not really train anything. Because if it is a support vector machine, you have built the model, now somebody added another sample, you have to retrain again. But for support vector, for k-nearest neighbor, no retraining is needed. Disadvantages include when the training set is large, it takes a lot of space. Imagine having to calculate distance for every member, and I want to test. I have 10,000 training sets, and I have 3,000 testing sets to check. That's going to be huge memory and also computational time. Because for every test data, the distance to be computed between test and all the training set. Therefore, a lot of time may be needed for the testing. That is the concept of this algorithm. Tips for us: KNN perform better with a lower number of features than many features. They say when your features are not many, it may perform for you. Again, don't forget what I tell you, always let the data speak. A lot of established factors in the past are no more working because since things are changing. That someone, a medical doctor was telling me, say in the past that blood pressure that was acceptable used to be 198, 190 against maybe 140. He said later it became 160 against maybe 120. Later it became 140 against 100. Now it is generally believed to be 120 against 80. You see, because the system keeps changing. Our great-great-grandfathers, what they were eating is different from what we are eating. The life they are subjected to is different from ours. So things are changing. You see, in similar way, what worked for people 10 years ago in KNN may not work on the data set you are having presently because the data set is coming from a different set of generation of people that are used to different mode of life. So research has shown that large dimensional Euclidean distance is not useful anymore. That at large dimension, Euclidean distance may not work for you. You have to try Minkowski distance. But I always say, let the data speak and let the empirical result decide for you. Okay? Sometimes we have cosine similarity measures. So, and other measures we might use. So, data set is small, it's advisable. Data set is small, use KNN. Data is labeled, and data is noise-free. These are some of the advices are tips for us, but they are not categorical. That without it, that you cannot get a result. Yes, that is k-nearest neighbor for us. That's the theoretical background of k-nearest neighbor, and I hope we all follow. Now, I would like us now to demonstrate practically. Yeah. So naive-Bayes classifier, if you have time later, about tomorrow, we can delve into this. We still have decision tree also we have for that. Otherwise, we can always check out our videos on naive-Bayes in our YouTube channel, how it works practically, especially if you want to go into the theoretical basis of how it works, and because you want to build your own in future, that is fine. So now I'm going to go into the practical mode. Let us now demonstrate for ourselves how we can use Weka. Now, this is the Weka application I want us to use. I want to believe we are seeing my screen. So you can chat, please help me type there if you can see it. Can you see a board, a software that is having board as their logo? Can somebody chat back if you can see it? Yes, okay, that's a good one. Thank you. Yeah, so once you get to Weka, you click Explorer. You click Explorer. And then you bring in your data in. Explorer will bring in your data. Once you click Explorer, it will open. So you see Weka is there. Here, this is the Explorer. Now, okay, I click it 2 times. Okay, so it has opened 2. I can minimize one of them. It's good news you can work on different data at the same time. You know, you can open as many explorers as possible. Working on this data, working on this data. So once you open it, there are different things you can do in the Explorer, but for a starter, I explain to start with Explorer. There's Experimenter. That one is more detailed. You can set up bash operations that you can click and go and sleep. I need to run it and you come back tomorrow and take your results. Okay? Those one also we can see them. If we have time, we will cover it. Otherwise, you can always see them check them out in our YouTube channel. We already covered it. So you open the Explorer as someone who's just starting. There's something also I will mention. Let me mention before I forget. There's 2. You call something package manager. See, package manager. Sometimes what you want to use is not inside your Explorer. So you can click Package Manager. Package Manager, when you open it, it will allow you to download new tools that are not present in the one you install. You can see here, this is Package Manager. I want support vector machine, SVM. You search it. It will bring you SVM library, LIB, SVM. So SVM attribute evaluators. So if maybe I didn't see this one in my Explorer, I'll click it and now say install. So it will bring it into my Explorer so that I can use it. That's one tool that is very important for us. Now let's go to the Explorer first. We're in Explorer now. The first, you can see everything is gray out. You can't do anything until you bring in your data set. That's the first step. Bring in your data set. Now, I'm going to open my data here. Open. So I'll go to my data set. You can see here that you can't see any data set here because Weka by default is expecting ARFF data file. .arff. That is the default value is expecting. So you need to change here. Click this data extension and change it to CSV. I want CSV file. You can see it will populate the place now with all files that are saved with .csv. Because CSV is what we are used to. See, we are used to the CSV file. This is it, for example. Let me open this file for you to see. This is a, I believe you must have seen this now. This is a data set to classify if somebody is diabetes or not, based on questionnaire. No medical test from any clinic, just set of questions. Age, what's your age? Gender, male or female? Weaknesses, do you experience weaknesses in your limb, in your body? Visual blurring, do you experience any visual blurring? Itching, do you always have itching? Delay healing, when you happen to have any wound, is it taking longer than expected for it to heal? Muscle stiffness, do you experience muscle stiffness? See, based on this, we have data set that can classify if somebody is diabetes or not. Positive means diabetes, negative means non-diabetes. This is a very simple data. You put your data set in Excel and you save it as CSV. Take note. Otherwise, Weka cannot access the standard Excel file. It will not recognize it. So you browse, you see where you want to put it, and then you can select. You can select it that, okay, I want CSV, comma, delimited. Yeah, you have different CSV, comma, delimited. This is the one you should save it as. We have CSV MS-DOS, CSV Macintosh. Save it as CSV, comma, delimited. Not the classical CSV. If you save it as Excel workbook, Weka will not see it. So let us take note of this. So once you save your data as such, the name, testing. Okay, now you save your data. You know, ordinarily you open standard Excel and you put your data in the Excel file. Now you save it as .csv. This is very important. So now we'll be back to, let's go back now. We have seen the data set. Now we're back to our Weka Explorer. Now select the one we want to use. We have different data set here. Let's deal with the one I just explained to us now, the diabetes interview-based predictive solution. Now, the data is now inside. You know, the moment the data arrives, you see something there. You see those things that were gray out before became activated now. I can visualize. I can select attribute. I can do association rule mining. The one I told you before in the morning, association rule mining. I can cluster. I can classify. So we are going to look into classification. First of all, foremost, let us let's look at it. This is pre-processed. This is the data. When you click age, it tells you the statistical characteristic of that column. Age. Minimum age there is 16. Maximum 90. Mean standard deviation. Sometimes you need this information in your report. You want to know the statistical analysis of your data set. Gender. Female. Male. You can see majority are male. Female, 192. Weaknesses. You see how many people reported weakness as yes? How many say no? All these are called descriptive analysis of the data. Visual blurring, itching, delay healing. How many people say yes to that or no? You can analyze all this. Now, the final class, what you want to predict is positive or negative. 320 people are positive, negative, 200 people. It means 200 people says they are confirmed not to have diabetes. But 320 people have diabetes. It's a very strange data set. Most data sets, usually, you have healthy people more than people that are having the sickness. But this is a special case because it is a questionnaire base. So initially, they targeted the people who have the disease. They went to a clinic. On the permission of the doctor, they were interviewing the patient who are confirmed to have diabetes. 320 people were interviewed. Then negative, they have to also interview people who are not diabetes, so they couldn't get up to that one. They got only 200, which is okay. The data is imbalanced, but the imbalance is not something huge. It is when you have imbalance of maybe 1,000 against 100 or 50. That became super imbalance, and then we can handle it. We'll talk about that one also later, inshallah. Now, so this is the data set. We're just analyzing the data, looking at it. So now it's time for you to go to the classification now. We are ready to do classification. You go inside classify. The first thing you have to do is this. Remember, I said when you want to build your model, you bring in 70% of your data set. Let's assume I have 70% of my data in the file I uploaded. You see? You bring in that 70%. So we can use percentage split to check how we are doing. So I want to use 70% training. And when you say 70%, we want to use split method. 70% training means 30% will be used for testing. And then I need to select the algorithm I want to use. So I want to use k-nearest neighbor. This is the one you are familiar with the way it is working. K-nearest neighbor is what I want to use. I select it. It is called, just put your mouse over it. It will tell you the name. K-nearest neighbor classifier. You see, put it below. So you can see where you belong. So I will click IBK. It's K-nearest neighbor. You can read about it, a lot of things inside it. So I'll click it. Now it has selected the IBK. So if I click start now, it's ready to run. But let me clarify something for you. See, you can see here that class, what we want to predict is class. It's automatically selected because in my Excel file, if you remember, in my Excel file, I make sure that the class is in the last column of my CSV file. Last column, rightmost side. Some people, they put their target class in the first column. There's nothing wrong in that. But if you do that, you must remember to come specifically, you have to remember to come here and select, okay, I want to predict age. Let's say I wanted to predict the age of this patient based on the other characteristics. I have to come here and say, please, age is what I want to predict. You can see it will change it to age. Otherwise, by default, Wika will pick the one on the rightmost side of your file. So that's why I always tell people to my own work, because sometimes you may forget. I've seen people forgot, they put what they want to predict in the first row, in first column, But when they got to weaker, they forgot. And they were predicting wrong thing, reporting wrong thing. When I saw the result, I said, something is not adding up. What are you getting? Look at your output. So then we realized he was predicting a wrong variable. So always remember this. To avoid forgetting, I always recommend put your class, the target class, put it in the last column of your Excel. It doesn't cost you anything. Just copy it and paste it there. So that even if you forget, you know you are not doing a wrong thing. Very important. Now the class is automatically selected. We want to divide into 70, 30. So when you click, it will run the experiment. It's using k-nearest neighbor, 70% for training. The one is showing for us here is the testing set. It will not show us this training set performance. It's using 30% for testing. This is the one you are having. If you want it to show you the testings, the training set, you have to click here, more options, and you have to go here and say, see, output model for training split. You click here, you check it, because like I said, training set is not our target. Our target is the testing set. Is it doing fine on the testing set it has never seen before? If yes, successful. So usually by default, it's not displayed. See, another thing also you may want to show is, I want to show the kind of classification it is having. Here now, it just gives us the summary. You see, correctly classify instance 136. Incorrectly classify instance 20. So percentage accuracy 87. These are other performance measures. True positive rate, false positive rate, precision, recall. This is the confusion matrix, which we are going to explain detail later. Confusion matrix is a way of really checking if your classifier is doing really great, if it's doing great or not. So, because sometimes you may have very high accuracy, but yet the result is not very good. So here, it's correctly classified people who have diabetes. 94 out of them were classified as having diabetes. We call it true positive. 10 of them, they are having diabetes, but they are classified to be having no diabetes. That's a mistaken one. See, that's a mistaken one. Whereas for this one, 42 people, they are not having diabetes. They classify them as not having diabetes. But 10 people who are not having diabetes have been pushed to classify as having diabetes. So this is called false positive, what we call false negative here. False negative is more serious than false positive. But false negative means somebody who is sick, you say he's not sick, he will go home and he may develop complication. But when you predict somebody that is not sick, has been sick, he will go to the clinic for further check. Of course, you are going to waste his time. They will check him and they say, oh, sorry, our AI system made a little mistake. We are sorry for that. You are okay, you can go home. That's a mistake. No mistake is acceptable, but one is more costlier than the other one. Imagine telling somebody you are okay, meanwhile it's not okay, and then you develop complication. That's some of the ethics of AI. Who is going to be held responsible? Is it the medical doctor who owns the hospital, or the AI that did the misclassification? Those are some issues to look into. Anyway, so now we build our first model. Now, let's say I use cross-validation, because I assume I brought in only 70% of my data. The 30% is outside. The 70% is what? It's outside. The 30% is outside. So I will use cross-validation to check my hyperparameters. See, with cross-validation now, it's using the entire data. It doesn't divide into two down. The full data I brought in, which is like maybe 80% of my data or thereabout. The 20% is outside, the testing set, which I'll bring in later to check how it is performing. Now, this entire 80% of the data set that we brought in is using 10-fold cross-validation, and it's getting me 92%. You can see and remember, it's going to run it 10 times and find the average. So whatever result you are having here is average. So then I can start modifying my data. This k nearest neighbor. The default value is 1. See, okay, let me clarify something for you. When you select an algorithm, how do you know what hyperparameters to tune? It will list it here. K is equal to 1. And then the weaker distance measure is Euclidean distance. These are the two things you change in k nearest neighbor. First is k, very important. So I will go in there, I click here, it will bring this one out for me. I change this k is equal to 1. I want to change it to 3. You want to check the Euclidean distance, you see it here. It's using Euclidean distance. You want to change it, I can change it to Manhattan, Minkowski. Shape distance also is there. But let's leave Euclidean distance for now. So I've changed the KNN to 3. I say, okay. Let me now run the experiment. Maybe it will improve my result from 92%. Let's see what we get. It went down. From 92%, it went down to 86%. Meaning, k is equal to 1 is good for me. Okay, let's check 5. Maybe 5 will be better. Who knows? Can you see? It's even going down. Down and down. I always recommend for people, try to have your result in Excel. Okay? 92, it became 86, now 81. So k is equal to 1, got me 92. K is equal to 3, got me 86. K is equal to 5, got me 81. If you have the time, you can run it more and see really what is happening. At 7, maybe it's taking you down also, or it's increasing. Can you see? It's going down. 79. Then that tells you that as the number of k is increasing, you are getting bad result gradually. It means I can conclude that for k is equal to 1 is good for me for this data set. I may go inside again and try to play with the distance measure. Let me choose shape distance. Maybe it will make a difference with 7. 79, the same value. Okay, let me put k is equal to 1 with shape now. K is equal to 1 because this is the one that gave me the best result with shape distance measure. Is giving 92 again. We can see that the distance measure does not make much difference in these data. So I will try other distance measure. If nothing is really giving me better than what I have, I can then conclude that Manhattan distance and k is equal to 1 is the best for this data set. At that point in time, I will now build a final model. Pay attention to this, please. I will now supply the same data that is inside 80. I'll bring it in now, fresh, because I want to build a final model. I know the k that is good for me. I know the distance measure that is good for me. Now it is time for me to build a final model. I'll supply the training set. I'll use the training set. That is the entire training set that is inside this system. All the data, the 80% I brought in. I'm not using cross-validation or whatever now. I've built a system with all the samples. Not using cross-validation, not partitioning. Once I build once I build the system, then I will now say supply test set. Supply test set. This one I'm going to now click and bring in my test results. Sorry, my test set that I already reserved, that has never been used anywhere. I'll now bring it into the system to see how well it will perform. And see how well it will perform. You now click start. Now it will use the test set to check the performance of your algorithm, the model you have built on data set that has never been seen before. This is how we build. You build your first machine learning model in weaker environment. Remember the process. Bring in the data, open your file, go to classify, select the one you want to use. Today, we are practicing IBK. We have others. This is lazy classifier family. You go to function. You have multilayer perceptron there. Support vector machine, SMO. See, down you have rules, 3. We have decision tree, decision trump, J48. These are random forest. These are three families. See, they are these three families. And also we have meta models. Those are ensembles. When you want to build ensemble machines, Ada boost, bargain, multi-class, random subspace stacking, voting, and also further ensemble. We have them inside the meta classifier. So whatever, if there's any algorithm you want to use that's not there, just go to your tool. Don't forget the tool. You open the package manager and you search for it, and it will bring it out for you. If when you want to work with deep learning for image classification, you have deep learning for Weka for those who work on the image classification systems. So this is just a short practical demonstration of how you can really implement your first model in the Weka environment. I think at this point, we will give room for people to ask questions, because I know they may want to have classification on this. Yeah, or depending on how it is. There are no, yeah, this is the data. You have the data already. I think I show you the data. Okay, I will open it up now so that we can raise questions. Thank you very much for listening. So the time also is going. So I'm going to give room for you to ask questions, but you want to seek clarification. Thank you very much.
Thanks so much once again, Prof, for that wonderful session. As to our members, please, if you have questions, you either raise your hand or you put it in the chat box. I think Prof will enable us to ask our question directly if you want to ask it directly, or you put it in the chat box. Why we are doing
Okay, so I already enable people to answer, and we will call them one after the other. Usually also put up the recording so that people can benefit. Now, the first person there that I can see your hand up is the engineer Blessing T. You have the floor. Engineer.
Thank you very much, Prof. I really appreciate the training.
You're welcome.
I want to ask I'm just concerned about the supply test set. Is it the same data we use from the beginning we are going to use for the supply set test?
No. You see, your test set, you must have extracted it totally from your data. Okay? You must have extracted the test set from your data. Let's say I have like 1,000 samples. I take 200 samples out of the data set away. I will make sure that I take in such a way that they are randomized and they are representative of each classes. So you take them out, you put it in one Excel sheet. Sometimes even your client will provide that data for you. They say, this is your test set. They give it to you separate from the training set. They say, this is the one we want you to use for testing. It's like 200 sample only inside it, containing both classes, positive and negative. You keep them away, keep it away during your training process. Then the remaining 80%, you don't even know the percentage because they just gave you training set, which is 80% of the data they are having. You now bring that one inside. Is it that one that you have the liberty to either use cross-validation or to use percentage split to do your hyperparameter modeling? Because you have to do hyperparameter tuning on your training set. Training set only. So that's why I use percentage split initially and also use cross-validation. And I use that to change what is the value of K. What's the value of K? Once you do that, now you now build a model. That is, you now say, bring me my training set, bring it in. The entire training set now, you now bring it in because you already understand the hyperparameter values that are good for you. In this case, you will now run the model, you now build the model using the entire training set. Then after that, you now say supply test set. You now bring in the test set that you want to bring in, which has never participated in the training procedure. I hope that answers your question.
Yes, but I'm concerned about
Hello?
the. Yes, sir. He answered to some extent. But
Okay.
is there any way we can, if I am the one that got the data by myself, is there any way I can segregate the data, the 50, 30 set and 70 set without bias?
Well, there are a couple of pre-processing methods you can use, actually. Yeah. So you can, please, Jamal, please, can you move? Okay, yeah. You can do that inside the Excel file manually. Try to see it, and there are software also that can do it for you. That also, you also. Jamal, please. We keep muting you. You are disturbing the class, please. Yeah. So you can do it either manually or you can bring it into even Excel. It's divided into training and testing for, and then you can save the testing set or the training set as a separate file later. So there are ways and many options that you can use to actually divide your data into training and testing. You have to ensure two things. It is randomized and also it is stratified. Stratified means you don't have a sample that has only positive, where it doesn't have any negative class in the testing set. That is a disaster. Okay? Yeah. Then we have Bolanle Akinboro. You have the floor. You can unmute yourself. You can allow you to push yourself. Unmute yourself. Bolanle Akinboro. Are you having problem unmuting yourself? Okay. Now we started hearing you little. Go ahead.
Sir. Thank you so much, Prof, for that wonderful teaching. My question has to do with the Weka application now. Now, how do we go about the step-by-step installation? Because I noticed we have it, the link has been posted to our email. So after the installation, then how do we get to the Weka Explorer? Thank you, sir.
Yeah, thank you very much for this question. It's quite very straightforward. Once you have the link was provided for you in your email, just click that link. It depends on the kind of machine. Once you go to the link, you select the one that matches your machine. The one sent to you, I believe, yeah, you see there, are you using Windows 64-bit? In the past, you used to have 32-bit. I think most of the system these days now are almost 64-bit. So you select, if you are using Macintosh, you select the installer for Macintosh. If you are using Ubuntu or Linux, you select it. But most people, they use Windows, that's fine. So once you get to that website, click it, it will download that Weka installer. Just double click the installer. It's self-installing. You don't need to do anything. Next, 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 next. Once it's finished, go to your program opening. Here, you can see here, just press the Windows sign. You can see my screen. Just click Weka. Click Weka, it will bring your Weka. I'm having Weka 3.8.6. I believe maybe today they may be having already 3.9 something. So if you install the latest one, that is fine. So you click it, it will open this, what you have here for you. It will open this for you. Once you install, click it, it will open this for you. This is the main window. And from there, you click Explorer. Click this Explorer, and then click the Explorer. If you bring something like this out for you, an empty space for you to play with. Yeah. You see, everything here is gray out now. You can't do anything because until you now bring out your data set. You can open database, you can generate your own data, artificial data. I don't do that. I better get it online than generating data, but some people like to do that. You can also open URL from online, but you must be connected and you trust your internet. But rather, it's easier to bring your data to your local machine. You open and go to the location where you have your data. Another thing you may face is go to where you have your data. I have my data set here. There's no data that's here now, you can see, because Wika is expecting .arff. My own data is stored as CSV. So you have to go here, click this, and tell, show me CSV data files. Then it should start showing other samples as you have. It will start showing other samples as you have. You have scroll data, open the one you want to work with. So you see hypertension, we are working with this guy, interview on this. You click it, it opens. And then you can start exploring your data as the case may be. I hope that answers your question.
Yes, sir. Thank you very much, sir.
Okay. You're welcome. Thank you very much. And I seriously encourage everybody to have the system data, to download the data before tomorrow. Try to practice something. Get data. We put this same data, we put it on in the platform. At least use it to be able to run something. For the first time, I want you to run your own, build your own model on your own computer. And then from there, you can bring your own data set in, as the case may be. The other questioner is there is Salahu Musliu. You have the floor.
Thank you, Prof.
You're welcome.
For this wonderful teaching. May God bless you, sir. Jazakumullah khairan.
Thank you very much.
For we, the beginner, as far as this modeling is concerned, my first question is concerning the training data and the test data. So I understand that we are going to have the test data out of the training data. We are going to extract it from it. Now, how are we going to, is there a particular range of value that we are going to be having to confirm that our training is robust? Or I don't know how to really put it. To know that what we are having is good, then we can bring in any new value to now test the data. And if we now use our test data, it's like I want to believe maybe the way I understood it is the test data is going to be as if we want to now test our training data if it works. Then if it's true, what are the characteristics that we are going to see? Is there a particular value that it's going to show us? Maybe I didn't get it during the course of explanation. Thank you, sir.
Thank you very much. Thank you for that very nice one. Yeah. Thank you very much. Now, let me make it clear here. You see, now you have a training set. Okay. This is the new data we just brought in. Okay. Okay. Let's use the existing one. Yeah. We have one here. Where we have already did some training on it. That's fine. Under classification. Yeah. See, when you have your data set already inside, just want to show us something there. Yeah, here. Okay, I have this Explorer where we work. You can see all the previous training I've been doing, they're out there. You can always click. You can always click it. And the good, you can save the model. You want to save it for future use, you can save it. You can visualize. So, and view in separate windows and other things. However, following your question, if I understand it clearly, we want to know at what time do we know that, okay, it's okay for me now to bring in my test set? Yes, that is when you think your training is now okay. Remember, we were using cross-validation on the entire set. So, and we were checking using K, we got in 92.5. We tried to do more. Can we get something better? Can we do pre-processing? A lot of pre-processing stuffs that could be done. So I don't want to start with those ones. I don't want to get too confused. The most important is to, first of all, understand how can you build your first model. See, we have different ways of processing, attribute instances, and also others. So whereby you can clean your data, you can do normalization and the likes. But the most important thing is to make sure you follow the lay-down principles. Through the cross-validation, you have done the hyperparameter optimization. You check for all possible K values. One is the best for you. You check for all possible values of a distance measure, Minkowski, Chebyshev, distance measure, and others. There's nothing you can do again. Now you are getting 92%. And to your client, this is more than enough. I remember I worked for some people one time. We were getting 75% accuracy. I was not very okay with that. I wanted to work more. And the man said, no, this is too much. We used to use statistic. We were getting 40 and we were publishing. Now getting 75 is even too much. Let's go ahead and write. He said it's enough. At that point, we stopped because that was the request of the client, that what they are getting is more than enough for them. So in that case, let's say 92.5, the person worked on this problem before, achieved 83. Now you have achieved 92. You can see that, oh, if I trade with the entire system and it's able to give me 92, now it's time for me to bring in my testing set. If your testing set now arrive and you are able to achieve like 90 or 87 or 89, better than what the best person got before, then at that point, you know, yes, what I'm getting is reasonable. I think I can stop at this point in time. So it depends on the condition placed on you by your client. And if you are the one doing it yourself, what do you want to achieve? We do a lot of comparative analysis in machine learning experiment. Somebody already worked on this same data set online. He achieved 82%. Now you have achieved 92%. That's acceptable achievement. If you can do more, you do more. Otherwise, bring your test set and then be able to establish that, yes, it is time to start writing my report and do the needful to it. So it depends on what you are solving, the problem you are actually handling. That will determine, okay, is the percentage accuracy okay? You also look at the confusion matrix. You know, we are still dealing with classification problem. Hopefully tomorrow we'll be able to demonstrate a regression problem, by the grace of God, where we also look into one regression problem at least to see how you can also predict things that are not yes or no. So you can also check look at this now, 298, true positive. People who are sick and predicted to be sick, they are 298. 183, people who are not sick and they are predicted not to be sick, they are 183. 22, these are people who are sick but are predicted to be healthy, to be good guys. 22, people who are not sick but are predicted to be sick, they are 17. This model is still having problem because the false negative is more than the true false positive. I told you before, when you predict that somebody is not sick, meanwhile he's sick, it's a serious mistake. We don't want it. Then at that point, we may start thinking of bringing in new algorithms. If K nearest neighbor cannot be improved anymore, then we may have to bring in a new algorithm that may help us model this in a better way that can reduce this number of positive misclassification to negative. 22 patients have been classified as healthy. Meanwhile, they are not healthy. So if you feel that we still need to do more because it's not acceptable, then KNN is no more working for you. Maybe it's time for you to bring in our friend decision tree. I bring in D48 and I can start the modeling and see what it can bring out for me. D48 also is even going down. Maybe it's time for me to consider their big brother function, support vector machine, SMO. It will take time, depending this is get it down. Then we start the hyperparameter optimizations and also for that we can do. So you have that liberty. You have several algorithms you can try out to see which one is going to work for you. It is after you have done see that, okay, I think I built the one that is more than enough, acceptable. Then you bring out the final testing set that you have extracted separately to come and help you finally decide the final output you are going to report. I hope that clarified. Mr. Salahu Muslim.
Thank you very much, sir. To some extent, but I want to ask Prof. Sir, is there any textbook or a kind of manual that one can read to better the understanding of all this procedure, so that by the time we are practicing, or we give like a kind of workflow to have, okay, from one step, by the time you want to send this test, data for us to practice, so be able to do the following as it is, so that we'll be able to get it done.
Well, it's okay. So those who like to read text, however, I think the easiest way is the videos will be made available for everybody, okay? You can just replay the video and see how we practicalize it, okay? I believe that
would
would be
the video be made available in earnest so that we'll be able to practice
yes.
tomorrow?
As we are finishing, you'll see the link to the video, okay? Don't worry.
Thank you very much.
You are welcome. So that you can always replay and then you can get this done. I want
Okay.
everybody.
Sorry, Prof. Can I still go ahead?
Hello?
Hello, sir.
Hello?
Hello, Prof.
Hey, yes, I'm hearing you. I'm listening.
Okay. Where you check for the where it is given the value for those who are not sick and it's reporting them to be sick, when we use another algorithm, it's giving like 80, 90, 56.
Yeah, because another algorithm is going to work in a different way. You can see now, okay, let's look at the one here. This is a decision tree. It's getting 73%. Remember, KNN was getting 92. Now, more mistakes are coming in. Instead of 22 false negative, that is making us not to adopt that one. This one is getting 80 false negative, more mistakes. So I have to do hyperparameter optimization for decision tree. If at the end of the day, I'm not getting better than that one, I may have to go back to my k-nearest neighbor that gave me better result ab initio.
Okay.
And only 22 mistake in the bad side. You get the point. So that's why
Yes,
you
sir.
use different algorithm. Go for the one that is working for you at the final level. And that is why I said we should not configure ourselves to only one algorithm, deep learning, support vector machine. No, start from simple one. Now KNN is showing us that it can get better result for us, even than sophisticated algorithm may not be able to get. It depends on the nature of the data set. Okay?
Thank you very much, sir.
You're welcome. So thank you very much. I believe those are the people who have questions. Few questions were up. Yeah. Okay, thank you very much. Mr. Ali Olawale Abdurasaq, he said, watch Prof video on YouTube, very informative. I refer us to, like the coordinator said today, if we can, it's just to kind of motivate us and introduce us to it. We have so much resources on our YouTube channel that and every week, every Saturday, we meet to clarify whatever question you are. You're always welcome to join us. 7:30 a.m. to 8:30 a.m. Nigeria time, every Saturday, except if maybe I'm traveling or have some other appointment. So somebody say, I want to understand how does algorithm work. For test data set, does it remove the target feature during the process and come back later to check and compare? Yes. You see, by the time you are testing, it's a code, it doesn't check the output of the target. It doesn't check the target. It will be using the input and generating its own target, its own prediction. It will now put the original target side by side and compare it. Am I getting better result compared to this? Let me show you something in the weaker. Let's say here, I go here, more option. I say, I want him to show me the prediction. Show me prediction in plain text, please. And now I run the model again. Can you see now? It's not just showing me the result only. It's showing me the output. This was the actual output we have, positive. This is the predicted output, positive, 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 positive. Then when you have error, positive, negative. This is the prediction. It predicted negative instead of positive. So it will, while doing it, it will now check the output. It will predict its own output and now bring the output side by side to compare for us to be able to see if it is actually correct. This is how it is done. Thank you, sir. Yeah, hope that answers your question. Okay, watch Prof. Jazakallah khairan. Thank you, sir. Can we use the data that the items has been coded, or we use it as raw, spread from the online data collection to that? Yeah, you see, if the data set is already coded, go ahead and use it as it is. Pray, hoping that you get good results. But sometimes the coding may have makes some important insight to be obscure from your data. But let's hope you are going to get the coded one performing well for you. If it doesn't perform well, it is time for you. If you can get the raw score before it is coded, you can bring it back and try to see maybe the raw score will work for you. We had a PhD person here who defended recently. Congratulations once again. He was working on data that had been excessively preprocessed. He couldn't get what was expected until he joined our daily weekly program, and he heard about the idea of letting the data speak. He went back and used the original data. He was able to achieve what he couldn't achieve. And that thing has stuck his PhD work for long. To God be the glory, he defended his PhD successfully. So this is the idea. If your coded data is working, so congratulations. But it's not working towards what you are looking for, it may be better to bring back the actual data before the raw score. It's like somebody working on normalized data. If you are getting a good result, excellently well, that's fine. But if you are not clicking what you are expecting, go back to the original data set, let the data speak. This is very important. I believe, okay. Thank you for the impactful presentation. My question are, can Weka tool do data preprocessing like PCA? Yes, I show you there. You have preprocessing option there. PSO, they are there. Can testing data differ from training data? Ask 5 features and test. No, they are going to be error. Your testing data cannot be different from your training data. Thank you very much for this question. If your training data is having 6 features, your testing data must have 6 features. You can't have different features for training and different features for testing. It will generate error, okay? Because the training set is not magic. It has generated some equations or some model that is considering 6 features. If you bring in 5 features, it will not work. It will lead to error. If the training testing set available are only having 5 features, you have to go back and build a new model that is using 5 features, the same thing as those 5 features you want to bring in. Okay? Yeah. So how do you bring an external validation inside the Weka? I say you use supply test option. Click the supply test. Is to show you opportunity to open the file that is you are bringing in as external to the system. So Weka can do PSO, and anything you want to do in Weka that is not available, always remember, go to this tool, package manager, and the package manager, you search for it. You want to use PSO, you can't see PSO there, then search for it in the package manager and install it. You can see PSO. So PSO, can see PSO search is there. Particle swarm optimization. You can bring it in, you say install. Install. See? Okay. It's asking me to close all the Weka I'm using before it can install PSO. So I have to close all my explorers, everything about Weka before I can use it, can install it for me. So a lot of things that are possible. If it's not there in your own Weka, you can always bring it in. I think, please, I just joined some minutes ago. I didn't really understand the lesson. Well, this is deep. So we always encourage us to come very early. But then you can look forward to the videos that will be posted for us so that you can then be able to learn from the videos that are being posted. Okay? So yeah, can we use weaker software to handle spatial data set? It depends. Like I said, it has deep learning concept. It depends on the kind of spatiality you want to model. You see? Yeah, if there's any special characteristics, can you arrange your data in an Excel form that you can bring in? If yes, it will deal with it, depending on the nature of data that is there. Okay? To run into trouble, there are always a lot of help facility from Wika also we can consult, and we can also consult us accordingly. You can use it for spatial. I remember we won't publish a paper not long ago where we did some spatial analysis using Wika environment for the work. And which one should we consider most between the confusion matrix and the percentage? Well, they are going to assist each other. You don't just consider one and leave. You may be having 90, for example, as a very unfortunate case, we have 95% accuracy, even 99%. But the second class is not being classified correctly. You have seriously imbalanced data set, where class A is like 990. The class B is having only 10 samples. During the testing set, all the testing sets were classified, all the class B were classified as class A. No single class B was classified correctly. But yet, the system report 99% accuracy. Because the other class is so huge that it surprised the other. It is that particular, it is the confusion matrix that will now tell us that, hey, guys, no, you need to check confusion matrix. It's not hard enough. So sometimes you can have very high accuracy here, but this one is not good. The old AI, there's nothing here, it's zero. All of this is classified as this. That model is not able to classify the second class. Even though you're having maybe 98, 96, 92, you don't celebrate that. So you have to look for better algorithm or do your other optimization to make it better. So you have to look at the two. As you are checking the percentage accuracy, you're also looking at the confusion matrix. Sometimes also we check recall, precision. We'll talk about that one hopefully tomorrow under other performance measures. So don't check only one and go. We have to check the two together. Yes, again, at what point can we bring it a new sample to predict, the data that are not part of the train? Yes, you have the testing set. No, once you have built your model very well, then you loaded the model is already loaded. Just bring supply test set. You have another set that is coming in. Just supply this test set and bring it in. It will always classify for you. It will classify for you. Just say supply test set, it classify for you. In case you have a test set that you don't have the output, in the output, just put a fictitious value there. This one, it will bring it in, and then it will generate the output that is coming from your model, and then you can then decide, oh, is it reliable or is it not reliable? That is how we handle it. Okay, it's clear. Thank you very much. Thank you very much, everybody, for the time. I believe it's a good time to call it a day. Thank you very much. Over to you, our coordinator. Thank you very much.
Thanks so much, Paul, for the question and answer section. And we also appreciate our members for the patience. Although it's already 50 minutes or 60 minutes after our designed time, but we appreciate the patience. By God's grace, tomorrow we'll be meeting by 2:30, just like the second session of today. And we promise that all the resources used for today's sections will be posted on our platforms dedicated for the Easter one. I believe everyone has joined the platform, and if you know you are not there on the platform for track one, please raise your hand so that we can add you for you to be able to access the resources and other material that will be shared there after the program. Once again, thank you for coming, and see you tomorrow by 2:30 Nigerian time.
Coordinator, I think two guys are
Sorry,
ready.
I have not filled the the attendance form.
Let me share the link. It's already there, but let me share it.
Good evening, sir. Please, the data for the worker, the hospital data, please, can you send it to the group so we can work on it? Just so easy so you can practice on it, sir.
Yes, it will be done. It will be done right away, okay? So check your WhatsApp.